of minerals. All samples of a given mineral have the same crystalline structures and chemical compositions, which give them distinct sets of physical and chemical qualities. For instance, all halite specimens break similarly and have the same hardness and density. Physical characteristics that are simpler to recognize are usually utilized in identification because it is challenging to ascertain a mineral's interior structure and chemical makeup without the use of complex tests and equipment. Some of the physical properties of minerals used to identify it include color. Minerals are natural substances that form the building blocks of our planet. They come in a remarkable array of colors, each possessing its unique beauty and significance. From the vibrant blues of azurite to the fiery reds of cinnabar, the colors of minerals captivate our imagination and offer valuable insights into their formation and composition. This note explores the significance of color in minerals, highlighting its causes and the variety of hues observed in the mineral kingdom. 1. The causes of color in minerals. Chemical composition. The atomic structure and chemical composition of minerals determine their color. Various elements and impurities present in a mineral can absorb or reflect certain wavelengths of light, giving rise to specific colors. For example, iron impurities often contribute to the yellow or red hues observed in many minerals. Electron transitions. The movement of electrons within a mineral's atomic structure can also influence its color. When electrons absorb energy from light, they may jump to higher energy levels, resulting in the absorption of specific wavelengths and the reflection of others. This process gives rise to the perceived color of the mineral. 2. The diversity of mineral colors. Earth tones. Many minerals exhibit earthy colors, such as browns, yellows, and greens. These tones often arise from the presence of iron, manganese, or organic matter. Minerals like limonite and malachite exemplify these hues. Vibrant blues and greens. Azurite and malachite are copper-based minerals that exhibit gorgeous blue and green tones. These striking hues, which are frequently seen in gemstones and ornamental minerals, are produced by the presence of copper ions and their interaction with light. Radiant reds and pinks. Minerals like cinnabar and rhodochrosite showcase rich reds and pinks. These colors result from the presence of iron, manganese, or other transition metals. Additionally, the size and arrangement of atoms within the mineral can affect the observed hue. Lustrous blacks and grays. Certain minerals, such as magnetite and graphite, exhibit deep black or metallic gray colors. These hues arise from the high absorption of light due to the presence of dense elements like iron and carbon. 3. Geological significance. Mineral identification. Color plays a crucial role in identifying minerals. Geologists often rely on the distinctive colors of minerals as initial clues for their identification in the field. However, it's important to note that color alone is not always sufficient for accurate identification, as some minerals can exhibit a range of colors. Environmental factors. The environment in which minerals develop can affect how colorful they are. Geological processes such as pressure, temperature, and the existence of particular materials. Geologists can learn more about the history of the mineral's development by examining the color changes. Streak. The streak of a mineral refers to the color of its powdered form. It is determined by rubbing the mineral against an unglazed porcelain plate, which leaves behind a streak of powdered mineral. Streak color can be a useful diagnostic property in mineral identification because it often remains consistent regardless of variations in the mineral's overall color or appearance. Here are some key points about the streak of minerals. Variations in streak color. The streak color may be different from the color of the mineral's external surface. For example, a mineral that appears yellowish-brown may leave behind a green streak. Diagnostic value. Streak color can help distinguish between minerals with similar external appearances. It is especially useful when identifying minerals that have a non-diagnostic or variable coloration. Streaks are broadly categorized into two types: metallic and non-metallic. Metallic minerals, such as pyrite or magnetite, leave behind a streak that appears shiny and reflective. Non-metallic minerals, like quartz or feldspar, leave behind a streak that appears dull and non-reflective. Impurities and streak color. In some cases, impurities present in a mineral can affect its streak color. For example, quartz is typically colorless, but impurities can cause it to have a colored streak. It is important to note that streak color alone should not be used as the sole criterion for mineral identification. It should be considered alongside other properties such as hardness, cleavage, crystal form, and specific gravity to accurately identify a mineral. Crystal shape or habit. Crystal shape, also referred to as crystal habit, is the characteristic external form or appearance of a mineral's crystal. It is determined by the internal arrangement of atoms or ions within the mineral's crystal lattice. Crystal shape is influenced by factors such as the mineral's chemical composition, crystal structure, and growth conditions. Minerals can exhibit a wide variety of crystal shapes or habits, which can be described using specific terms. Here are some common crystal habits. Cubic. Minerals with a cubic habit have crystals that exhibit a cube-like shape with straight edges and flat faces. Examples include pyrite and halite. Octahedral. Octahedral minerals have crystals that resemble two pyramids connected at their bases. Each pyramid has 8 faces, resulting in a total of 8 faces on the crystal. Examples include magnetite and fluorite. Prismatic. Prismatic minerals form elongated crystals with parallel sides and often have a rectangular or hexagonal cross-section. Quartz and tourmaline are examples of minerals with a prismatic habit. Tabular. Tabular minerals have thin, flattened crystals with parallel faces. The crystals often have a plate-like appearance. Examples include gypsum and barite. Acicular. Acicular minerals have needle-like crystals that are long and slender. Examples include natrolite and rutile. Bladed. Bladed minerals have flattened crystals that resemble the shape of a knife blade. Kyanite and gypsum can exhibit a bladed habit. Dendritic. Dendritic minerals have branching, tree-like crystal formations. They often appear as intricate, fern-like patterns. Dendritic forms are seen in minerals like silver and manganese oxides. Botryoidal. Botryoidal minerals have rounded, globular crystal clusters that resemble a bunch of grapes or bubbles. Hematite and malachite can exhibit a botryoidal habit. Reniform. Reniform minerals have kidney-shaped crystal aggregates that are smooth and rounded. Hematite and goethite can display a reniform habit. It's important to note that while crystal shape can provide clues about a mineral's identity, it is not always a definitive characteristic for mineral identification. Other properties, such as color, streak, hardness, and specific gravity, should also be considered. Crystal shape is an important aspect of mineralogy as it provides insights into a mineral's growth conditions and the interactions of its constituent atoms or ions. By examining crystal habits, geologists can gain information about the formation processes, environment, and history of minerals. Tenacity. Tenacity is a term used to describe a mineral's response to mechanical stress or deformation. It refers to how a mineral behaves when subjected to external forces, such as bending, breaking, or crushing. Several categories of tenacity describe different behaviors exhibited by minerals. Brittle. Brittle minerals are those that break or fracture easily when subjected to stress. They tend to shatter or produce irregular, jagged surfaces upon breaking. Examples of brittle minerals include quartz and most silicates. Malleable. Malleable minerals are capable of being flattened or bent without breaking. They can be hammered into thin sheets or molded into various shapes without fragmenting. Gold and silver are examples of malleable minerals. Sectile. Sectile minerals are characterized by their ability to be cut into thin shavings using a knife or blade. They exhibit a property similar to malleability but are specifically related to the ease of cutting. Examples of sectile minerals include talc and gypsum. Ductile. Ductile minerals are capable of being stretched or drawn into thin wires or filaments without breaking. They exhibit a property of plastic deformation under stress. Copper and silver are examples of ductile minerals. Flexible. Flexible minerals can be bent or twisted without breaking. They have a certain degree of elasticity and can return to their original shape after the stress is removed. Asbestos is an example of a flexible mineral. Elastic. Elastic minerals can return to their original shape after being deformed by stress. They exhibit a property of resilience. Examples of elastic minerals include some types of mica and graphite. It's important to note that the tenacity of a mineral is determined by its physical properties, such as crystal structure, atomic bonding, and composition. These factors influence how the mineral's atoms or ions respond to stress and deformation. Understanding the tenacity of minerals is important in various fields, including geology, materials science, and mineral processing. It helps in identifying and characterizing minerals, determining their potential uses, and predicting their behavior under different conditions. Luster. In the world of geology, minerals captivate us with their remarkable diversity and inherent beauty. One of the captivating features of minerals is their luster, the way they reflect and interact with light. The luster of minerals provides valuable information about their physical and optical properties, making it an essential characteristic for identification and classification. This note explores the captivating world of mineral luster, shedding light on its importance and the various types of luster exhibited by minerals. Defining luster. Luster refers to the way a mineral surface reflects light. It is determined by the interaction of light with the mineral's surface and internal structure. The luster can range from dull and earthy to a brilliant, glassy shine. By observing the luster, we can gain insights into the mineral's composition, crystal structure, and surface features. Types of luster. 1. Metallic luster. Minerals with metallic luster exhibit the reflective properties of a metal surface. They appear shiny, polished, and reflective, resembling the appearance of metals like gold, silver, or copper. Examples include pyrite, galena, and hematite. 2. Non-metallic luster. A. Vitreous luster. Minerals with a vitreous luster possess a glass-like appearance, similar to the shine of a freshly cut piece of glass. Quartz and feldspar are notable examples of minerals with vitreous luster. B. Resinous luster. Resinous luster gives minerals the appearance of resin or fresh tree sap. Amber and sphalerite are minerals that exhibit this luster. C. Pearly luster. Minerals with a pearly luster exhibit a soft, iridescent, and pearl-like shine reminiscent of the inside of a seashell. Examples include talc and some varieties of gypsum. D. Greasy luster. Greasy luster imparts a greasy or oily appearance to minerals. An excellent example is nepheline. E. Waxy luster. Minerals with a waxy luster appear as if they have been coated with a thin layer of wax. Serpentine and some varieties of opal exhibit this luster. F. Silky luster. Silky luster gives minerals a fibrous or silky appearance, resembling the texture of silk. Satin spar gypsum and fibrous varieties of asbestos are examples of minerals with silky luster. G. Dull or earthy luster. Minerals with a dull luster lack reflectivity and appear matte, similar to the texture of unglazed pottery or a weathered rock surface. Kaolinite and limonite are minerals that exhibit this luster. Significance of luster. The luster of minerals serves as an essential diagnostic tool for geologists, mineralogists, and gemologists. It aids in the identification and differentiation of minerals from one another. Luster, along with other physical properties such as hardness, cleavage, and color, helps in narrowing down the potential mineral species. By carefully observing the luster, scientists can make educated guesses about a mineral's composition, crystal structure, and formation environment. Hardness. It is a physical property that measures a mineral's resistance to scratching or abrasion. It is one of the most useful diagnostic properties for identifying minerals. Hardness is determined by the strength of the chemical bonds within a mineral's crystal lattice. Mineral hardness is commonly measured using the Mohs scale of hardness, which consists of a series of 10 minerals arranged in order of increasing hardness. The scale was developed by Friedrich Mohs in 1812 and remains widely used today. The Mohs scale assigns a hardness value ranging from 1 to 10 to minerals based on their relative scratch resistance. The minerals on the scale are 1. Talc, the softest mineral on the Mohs scale. Talc can be easily scratched with a fingernail. 2. Gypsum, slightly harder than talc. Gypsum can be scratched with a fingernail as well. 3. Calcite. Calcite can be scratched with a copper penny or a knife blade. 4. Fluorite. Fluorite can be scratched with a knife blade. 5. Apatite. Apatite can be scratched with a knife blade, but not as easily as fluorite. 6. Orthoclase feldspar. Orthoclase feldspar can be scratched with a steel file. 7. Quartz. Quartz is a relatively hard mineral and can scratch glass. 8. Topaz. Topaz can scratch quartz. 9. Corundum. Corundum, which includes gemstones like ruby and sapphire, can scratch topaz. 10. Diamond. Diamond is the hardest mineral on the Mohs scale and can scratch all other minerals. The Mohs scale is relative, meaning that it compares the hardness of minerals to one another. For example, if a mineral can scratch calcite but not fluorite, it would have a hardness value between 3 and 4 on the Mohs scale. It's important to note that the Mohs scale does not provide precise measurements of hardness, as it is based on a qualitative assessment of scratch resistance. However, it is a widely used and convenient tool for mineral identification. Hardness is valuable in mineral identification because it is a property that can be determined with simple tools and observations. By testing the hardness of an unknown mineral against minerals of known hardness, geologists can narrow down its identity and distinguish it from similar minerals. Cleavage. Cleavage is a term used to describe the way minerals break along preferred planes of atomic weakness. It is a property that varies among different minerals and is often used as a diagnostic tool in mineral identification. It is a result of the crystal structure of a mineral and the arrangement of its atoms. When a mineral exhibits cleavage, it means that it tends to break along flat, smooth surfaces. These surfaces are parallel to planes of weak atomic bonds within the crystal lattice. The resulting cleavage planes can be observed as flat, reflective surfaces on the mineral. Cleavage is characterized by several properties. Number of cleavage planes. Minerals can have varying numbers of cleavage planes. Some minerals have only one cleavage plane, while others have 2, 3, 4, or even more. The number of cleavage planes is an important characteristic used in mineral identification. Cleavage quality. Cleavage can be described as perfect, good, fair, or poor, depending on the ease and cleanliness with which the mineral breaks along its cleavage planes. Perfect cleavage refers to clean, smooth breaks, while poor cleavage indicates irregular or rough breaks. Cleavage direction. Each cleavage plane is associated with a specific direction within the crystal lattice. The direction of cleavage can be described in terms of its relationship to the crystallographic axis of the mineral. Cleavage angles. Cleavage angles refer to the angles between the cleavage planes of a mineral. These angles can be measured and used to help identify the mineral. Cleavage is distinct from fracture, which describes the way minerals break when no preferred planes of weakness are present. Fractures can result in irregular, rough, or conchoidal, shell-like surfaces. Understanding cleavage is important in mineral identification because it can provide clues about the crystal structure and composition of a mineral. Different minerals exhibit characteristic cleavage patterns that can help distinguish them from one another. It's essential to note that not all minerals exhibit cleavage. Some minerals, such as quartz, have a property called no cleavage or lack of cleavage, meaning they do not break along any preferred planes. Instead, they exhibit fracture. Fracture is a term used to describe the way minerals break when no preferred planes of weakness, as in cleavage, are present. Unlike cleavage, which results in smooth, flat surfaces, fractures produce irregular, rough, or conchoidal, shell-like surfaces on the broken mineral. Fracture. It can occur in minerals for various reasons. Different types of fractures can be observed in minerals including conchoidal fracture. Conchoidal fracture is characterized by smooth, curved surfaces resembling the interior of a seashell. This type of fracture is commonly seen in minerals like quartz and obsidian, which have a homogeneous and glassy texture. Irregular fracture. Irregular fracture refers to a random pattern of breaks with no specific shape or direction. It produces rough and jagged surfaces. Minerals with irregular fractures lack a preferred fracture pattern and break in a haphazard manner. Splintery fracture. Splintery fracture is characterized by the formation of elongated, splinter-like fragments along the broken surface. This type of fracture is often observed in fibrous minerals, such as asbestos. Hackley fracture. Hackley fracture is characterized by sharp, jagged edges and surfaces with a somewhat hacksaw-like appearance. It is commonly seen in malleable or ductile minerals, such as native metals like copper or silver. Earthy fracture. An earthy fracture refers to a powdery or crumbly texture observed in some minerals. The broken surface appears dull and lacks the luster seen in minerals with cleavage or other types of fractures. However, fractures lack the characteristic smoothness and parallelism associated with cleavage planes. Understanding fractures in minerals is valuable in mineral identification and can provide insights into the mineral's physical properties, crystal structure, and mode of rupture. Characteristics of fractures. geologists can gather information about a mineral's behavior under stress and its potential applications. Density and specific gravity. Density. Density is a fundamental physical property that measures the mass of an object per unit volume. In the context of minerals, density refers to the mass of a mineral sample divided by its volume. It provides valuable information about the compactness and heaviness of a mineral and porosity. Minerals with higher atomic masses or denser arrangements of atoms tend to have higher densities. For example, metallic minerals like gold and platinum have relatively high densities due to their dense atomic structures. In contrast, minerals with lighter elements or more open crystal structures typically have lower densities. Density is an important property for mineral identification because different minerals have distinct density ranges. Geologists often use density measurements as a diagnostic tool to differentiate between minerals with similar visual appearances. Specific gravity is a dimensionless quantity that compares the density of a mineral to the density of water at a standard temperature and pressure. It is a ratio that provides a relative measure of a mineral's density compared to water. The specific gravity of a mineral is determined by dividing its density by the density of water. Since water has a density of approximately 1 g/cm superscript 3 at standard conditions, specific gravity is often denoted without units, as it is a ratio. For example, if the specific gravity of a mineral is 2.5, it means that the mineral is 2.5 times denser than water. Specific gravity is a useful property in mineral identification because it can help distinguish minerals with similar densities. Geologists often measure the specific gravity of a mineral sample using various techniques, such as a density bottle. It's important to note that specific gravity can also provide information about a mineral's composition or purity. Impurities or variations in mineral composition can affect the density of a mineral, resulting in deviations from the expected specific gravity.